In this question, there's a combination of work energy and collision. What happens is that this mass m travels down. This is the bow of mass m. It travels down. It picks up another object of mass small m at this point. The other mass sticks to this mass, and the combined mass rises to height h. We need to find out this height h given these data. Now, for solving this question, let us first analyze the motion of this mass m from point A to B. Now, from A to B, for m, work done by external forces is 0 because the external force is tension, and the tension is always perpendicular to the displacement, which gives the work done by tension to be 0. There are no internal non-conservative forces, due to which work done by internal non-conservative forces is also 0. There is work done by conservative forces, but that will be handled by the potential energy, which we take into account. Therefore, potential energy at A plus kinetic energy at A is equal to potential energy at B plus kinetic energy at B. Let us take potential energy equal to 0 at this level, at the level of B, for simplicity. Therefore, potential energy at A is equal to mgh. Kinetic energy initial was 0, is equal to potential energy at B is 0 plus kinetic energy at B. Let the mass m come down to level B with velocity v. Therefore, this is equal to half mv square. Therefore, we cancel m and m to get v is equal to root over 2gh. So, we remember this result. Now, let us handle the collision. This mass m comes down with a velocity root over 2gh. It collides with another mass small m, and the other mass sticks to this mass. So, this was the initial motion. The final situation is that these two masses stick to each other and collectively move together with a velocity v dash. So, since there are no other external forces acting on these two objects, there is actually an external force that is equal to the tension in the string and the gravitational force, but these forces are very small and their effect is negligible for the small duration of collision. Therefore, we can apply momentum conservation. Ethically speaking, momentum conservation is only applied on the system when the external forces on the system are 0. In this case, though the external forces on the system were not 0, but since they were so small, because conservative forces are small and multiplied by a small time interval, their effect is very negligible. Therefore, we neglect the conservative forces and we apply momentum conservation on this system to get the result m into root over 2gh, that is initial momentum. This is equal to m plus m v dash. Therefore, we get v dash as m upon m plus m into root over 2gh. Now, we know the combined mass of the system at the lowermost point. This is v dash. Now, again let us analyze the pendulum motion. This will rise up to the point till its kinetic energy becomes 0. Now, again from this point to this point, we can again apply mechanical energy conservation. By applying mechanical energy conservation from this point to this point, we get, this is B, this is C, potential energy at B plus kinetic energy at B is equal to potential energy at C plus kinetic energy at C. V dash is equal to m upon m plus m root over 2gh. We can write this potential energy at B is equal to 0 plus half m plus m v dash square is equal to kinetic energy at C is 0. Therefore, this is 0. The potential energy at G is m plus m gh. This m plus m gets cancelled. We get h is equal to v dash square upon 2g. By substituting the value of v dash from here, we get H is equal to m upon m plus m whole square into 2gh upon 2g. This 2g gets cancelled to give us the result H is equal to m upon m plus m into h. M upon m plus m whole square into h. By feeding in the values in this equation from above, we get h is equal to 0.05 meters. So final answer is the final height to which the combined system of m plus m rises after the collision is 0.05 meters.